Hello, hello and welcome to CS500 Design and Analysis of Algorithms. In this course, we will talk about advanced aspects of algorithm. This course builds on top of undergraduate courses like Introduction to Algorithms or Discrete Mathematics in order to get a new and broader perspective on this rich and seminal field of algorithms. Now, the course is called Design and Analysis, and we put particular emphasis on the analysis part. Namely, in this course, we will analyze algorithms beyond the traditional paradigm of worst-case running time. That's how you learned to analyze algorithms in introductory courses when you considered sorting or searching algorithms. But in this course, we want to go beyond that. We want to analyze algorithms beyond the only running time, taking into account also other measures of cost, such as memory use, and taking into account other ways of analyzing algorithms, such as average case or amortized case. So that being said, let me start by sharing the screen and showing you the slides. This course consists of 10 chapters. And we're here in chapter 1, where we do a brief recap of computer science and of previous algorithms course. I will give an introduction to the purpose and ways that we design and analyze algorithms in this course. And I will end with an overview of the 10 chapters that you can look forward to throughout the rest of this course. So let's start. Let's start with chapter 1. And chapter 1 will cover the following aspects. First, we'll talk a little bit about the philosophy of science, perspective on, particularly on computer science. What distinguishes computer science from, let's say, electrical engineering, although both arguably usually revolve around digital data processing technology. And we'll talk about the power of abstraction, which is well known in object-oriented programming, and there it's called information hiding. And we will see about the difference between hardware and mathematical data types and the pitfalls that can come with that difference. We'll re-emphasize the importance of asymptotic efficiency. We'll recall classes of asymptotic growth. And then we'll consider a particular example, namely sorting, as an example of some of the aspects that distinguish computer science from electrical engineering, namely problem specification and optimality of algorithms. Then we'll discuss how do we analyze algorithms and why do we analyze algorithms instead of just, running them and trying them. Finally, we'll talk a little bit about administrative aspects of this course and an overview of the other 9 chapters. And I will close today's session with some thoughts and remarks about its pedagogical concept and about the teaching philosophy underlying this and general courses. Okay, so let's start and dive right into the philosophy of science and particularly of computer science. Let me start with a brief historical reminder about the relations between computer science and electrical engineering. Let me start with a historical example, namely Alan Turing, who can be considered the father of theoretical computer science, because in 1936, he wrote and published this nowadays famous paper. In this paper, called Uncomputable Numbers with an Application to the Entscheidungsproblem, he introduced what we nowadays call a Turing machine. A Turing machine is a mathematical model of a digital computer. However, at that time, there were no such digital computers. So his mathematical conception went beyond what was available technologically at that time. Furthermore, he analyzed this model, namely he demonstrated its fundamental capabilities. For example, he constructed what we nowadays would call a universal Turing machine, a Turing machine that is able to simulate any other given Turing machine. Furthermore, he proved ultimate limitations of this Turing machine. Namely, he proved that what we nowadays call halting problem probably cannot be decided by any of these machines. And these three contributions in this single paper then led and provided guidance to motivation to engineers to actually build such a computer, to realize a mathematical model, because Turing had demonstrated how powerful it is in spite of being actually very simple. The primitive operations are very simple. So this provided guidance and motivation to engineers to actually implement such a machine. And indeed, 5 years later, in 1941, it was Konrad Zuse who built the Z3 computer and who became operational in 1941, the first actual universal digital computer, arguably. So the message here, first, the computer science investigation, introduction, and then the engineering building such a machine. Here you see Konrad Zuse at his later age in front of the machine that he built then. Another example is quantum computing. In 1994, Peter Shor developed what we nowadays would call a quantum algorithm, and he demonstrated that this quantum algorithm can factor integers in polynomial time, which no Turing machine or no other classical digital computer is known to be able to. Now, at that time, there were no quantum computers at all, 1994. But as Peter Shor demonstrated the capabilities, the power of such a hypothetical mathematical model computer, it set off engineers and physicists to start and try to actually realize such a computer. And you may have noticed and recall that since maybe around 2004, a veritable gold rush set off towards the goal of realizing quantum computers with more and more qubits and with longer and longer reliable running times towards actually being able to practically factor integers. So the question of quantum supremacy is still under discussion, but definitely engineers only started to try to build these quantum computers because of Peter Shor's theoretical development. So again, first there was computer science, and then engineering, electrical engineering followed up. It doesn't have to be in that order. Sometimes things also go in the other direction. For example, with respect to analog computing. The first practical general purpose analog computer became operational at Massachusetts Institute of Technology in 1931, and it was able to process up to 18 independent continuous variables. In 1936, 5 years later, MIT employed an operator for keeping this machine running, and that operator's name was Claude Shannon. And Claude Shannon started thinking about the capabilities and limitations of such an actual engineering-built analog computer. And again, 5 years later, in 1941, he published this nowadays also famous paper on the mathematical theory of a differential analyzer, where here, again, first introduced a mathematical model of such a computer. Secondly, demonstrated what this computer was able to solve, namely a certain class, so-called differential algebraic equations. And third, conclude that this computer was fundamentally unable to solve certain problems. For example, cannot compute the gamma function or the Riemann zeta function. So again, 3 contributions parallel to those of Turing, but now historically in reverse order, first engineering and then computer science. So the message I'm trying to convey here is about the close collaboration between computer science and engineering, but also about the clear or not so clear sometimes distinction between computer science as a science and electrical engineering as an engineering discipline. You may you may say that the purpose of engineering is to build something, to realize something, and the purpose of science is to formalize things, to investigate their ultimate capabilities, and to determine their fundamental limitations. Let me give you another example from thermodynamics, right? Imagine refrigerator, right? The refrigerator cools things down. So maybe you have some hot dish and you put that into the refrigerator, and the refrigerator cools it down. In order to cool this dish down, the refrigerator needs energy. It consumes energy. And this seems kind of a little bit paradoxical if you think about the hot dish has a lot of heat energy when you put it into the refrigerator, and after it's been cooled down, it has lost a lot of this energy. So where does this energy go? Wouldn't it be more reasonable to expect a refrigerator to produce energy by extracting the energy from the hot dish that you put into the refrigerator, and that it then returns after having extracted the heat energy? But no, the opposite way, the refrigerator consumes energy in order to extract energy, heat energy. Is this necessarily so? Well, engineers certainly have built good and more energy efficient refrigerators, but so far nobody has built a refrigerator that produces energy, right? And that is where the difference between engineer building these devices and science, like physics, like thermodynamics, becomes apparent, because according to the second law of thermodynamics in physical sciences, such a refrigerator that produces energy would be impossible. It would be a violation of the second law. It would be a so-called perpetuum mobile of second kind, and that is impossible according to thermodynamics in science. So this is another illustration of the difference between engineering on the one hand and science on the other hand in general. So that being said, let's now move on to computer science with focus on being a science as opposed to an engineering discipline. And I like to call this the virtues of computer science, of course, tongue-in-cheek. And also tongue-in-cheek are here the seven virtues from Christianity. Here you see a picture of Ada Lovelace, who is sometimes considered the first programmer. She would kind of program Babbage analytical engine, which was a kind of first rudimentary analog computer. And I mention these and collect these virtues as they provide some guidance on what distinguishes computer science from electrical engineering and engineering discipline. And these are 5 virtues. The first is problem specification. Specify the problem to be solved before starting to solve the problem. And as I said, we will give examples later when we talk and recall the sorting problem. The purpose of problem specification is to make it unambiguous what the solution is considered and what would not be considered a solution. Moving on to the next virtue is algorithm design. Algorithm design involves talking about the primitives that we can use to design an algorithm, the semantics, the meaning of these primitives, and the cost associated with these primitives. So let me tell you a short anecdote about that. So when I was a high school student, I would write what I considered the fastest sorting algorithm ever. So to this end, I studied machine language, Intel 86 machine language, and I would count clock cycles of each machine instruction and hand optimize all the code, hand optimize loops, so that in the end, I was proud and convinced now I have here the fastest sorting algorithm. And then I went to university and attended a course on introduction to algorithms, and I got to realize what I had implemented was actually bubble sort. So by far not the fastest algorithm. And all my clock counting and hand optimizing machine code was just in vain. And what is the bigger underlying reason? I had confused algorithm design with programming, with coding. And that's an important lesson that I want to pass on to you, because here in computer science, we design algorithms, and implementing and programming then comes after that. So algorithm design is not to be confused with writing a program, and also algorithm is not to be confused with a heuristic. And the major difference between an algorithm and a heuristic is that an algorithm must be analyzed. So let me also illustrate the importance of primitives and semantics in algorithm design before moving to the analysis part. So imagine, for example, you're asked to write design an algorithm in computational geometry. Now, in computational geometry, algorithms usually start by sorting the input data, maybe with respect to the x coordinate or with respect to the y coordinate first. So when designing an algorithm in computational geometry, sort is considered usually a primitive, one operation. However, sort itself usually, of course, has to boil down to more lower primitive operations, right? So when designing not an algorithm in computational geometry, but when designing sorting algorithms as in undergraduate algorithms, then sort itself is not a primitive, but what are primitives? For example, comparison of 2 elements and swapping 2 elements are primitives when designing a sorting algorithm. Now, going even lower, comparing two elements, of course, boils down further to comparing bit strings. For example, when comparing two integers of length n bit, then that means to compare two bit sequence of length n, starting with the most significant bit because it's lexicographical order, and then moving on towards the least significant bit until it's determined which one is the larger. So also comparing two elements can be considered as a primitive when designing sorting algorithms, but it can be considered as a compound operation, compound of many bit comparisons when designing the comparison operation itself. So the message to take home here is it's important to specify which operations are considered primitive when designing an algorithm and which are considered to be compound operations, or which ones we are supposed to create to realize from more basic primitive operations. Also, the cost of each operation is important when analyzing algorithms. For example, let's say multiplying two integers can be considered as one operation, but it also can, because it usually proceeds by, for example, adding several integers, it can be considered as a compound operation and thus assigned cost more realistically depending on the size of the integers that are being multiplied. Similarly, for adding two integers can be considered as one operation, but more accurately, it is incurs cost depending on the magnitude, on the binary length of the integers being added. So therefore, the analysis part is an important part that turns a heuristic into an algorithm, and analysis refers to two aspects. First, the correctness, and secondly, the efficiency. Correctness means make sure that the algorithm indeed solves the problem under specification. That's why the first item is so important. And secondly, efficiency, measure the cost incurred by the algorithm, cost as specified individually for each primitive, and then analyze what is the compound cost of the execution of this algorithm. And these two proofs, correctness and efficiency analysis, may, but not necessarily have to be formalized. It's just important that correctness is ensured and that efficiency is ensured, and empirical correctness, running the algorithm on some benchmarks, and empirical efficiency are not sufficient to turn a heuristic into an algorithm. That's one difference between electrical engineering and computer science. So, and finally, moving on to the last virtue, that's proof of optimality. So once you have designed an algorithm and analyzed an algorithm for the problem under specification, then try to prove that this algorithm is optimal, at least asymptotically. There is no more efficient algorithm. And if you cannot prove that, if you cannot assert that, then maybe there is a more efficient algorithm, and then maybe you should start over with the second item, redesign the algorithm, reanalyze the algorithm, kind of a meta loop until eventually you have found the optimal, provably optimal algorithm. But proving an algorithm optimal actually can be a very challenging problem. For example, the P versus NP problem can be considered as a case of whether contemporary algorithms solving the Boolean satisfiability problem in exponential time, whether these are optimal or not. So this can be a very challenging task to prove an algorithm optimal. But that's the four virtues of computer science. Good. So now moving on, as I've been emphasizing already, an important part of computer science is abstraction. So not coding, not writing programs, but designing algorithms, analyzing algorithms, their cost, as opposed to running the implementation program and measuring its running time empirically. And the reason for that is part of a bigger picture, namely that abstraction comes with tremendous power. Well, let me talk here a little bit about the power of abstraction. And to this end, let's recall that all your computer that you have at home or in your smartphone are built on transistors. Now here you see a picture of the very first transistor, famous. And now the operation of such a transistor, it's a semiconducting device, heavily relies on quantum mechanics. Here you see quantum mechanics of one atom with its electrons, but actually this is a semiconductor, which means it's a solid state object combined of literally billions of atoms. So this is a many body quantum system with billions of quantum systems. And basically, in order to really understand a transistor and thus understand your computer, you first need to study quantum mechanics and solid state theory of conduction and valence bands. Now, if you don't have studied quantum mechanics, of course, yeah, I'm kidding. You can still use a computer. And that's because all these details, quantum mechanical details, and function and how to build a transistor can be safely ignored and compiled into much simpler conception, first into such a case transistor, and then even further simplified into such a logical symbol, namely as a control switch, depending on whether there's a signal coming into the base here, the signal coming here either can pass or cannot pass. So it's simply a controlled switch, and that's transistor. And that's all, almost all one needs to know in order to go to the next higher step level in the abstraction hierarchy, namely combining these transistors to such a switching board. This in turn can be simplified by considering Boolean circuits, as you can see in this diagram, which ignore many aspects of the underlying transistors, such as the voltage range and also all the quantum mechanics that we've already forgotten about. Then these transistors are combined into more advanced functionalities, such as an integrated circuit. Integrated circuits are combined into such circuit boards. Circuit boards are further miniaturized into a central processing unit on a single chip. And these are connected to external devices via such a motherboard, including, for example, memory. And this is already the computing hardware. And again, basically, you need to know about all the details of your computing hardware, but power of abstraction allows us to be ignorant about it by hiding it behind the basic input-output system, by hiding that in turn behind device drivers, by hiding that further behind an operating system, and then, for example, write an object library as in modern operating systems, and writing code in a high-level programming language on top of that, where we can ignore all the lower levels due to the power of abstraction. For example, if you write a program in Java, it doesn't matter. You don't need to know. You're not even supposed to know whether it's running on such a desktop computer on a laptop computer. Furthermore, you don't even know, shouldn't even care about whether it's running on this operating system or this operating system or this operating system, all because of the power of abstraction. You can ignore all these details when you write Java program. And conversely, the Java program that you wrote can then easily be transferred and moved between different kinds of hardware and between different types of operating system. So compatibility and universal applicability of your Java program relies on the power of abstraction. So that's why in this course, we focus on the high level design and analysis of algorithms and ignore all the lower level details that engineers, electrical engineers have so well taken care of. If you think about it, the computer is an incredibly advanced pinnacle of engineering technology with nanometer technology clocked at gigahertz rates and working reliably for hours and weeks on such high frequencies. So that's really impressive, and we kind of take care of that by ignoring all the details and focusing on the high level. So that concludes power of abstraction, but let me also emphasize the caveat, namely sometimes there's an error arising from confusing hardware with mathematical data types. Mathematical data types being the abstract ones, and hardware data types, for example, bytes, are the ones coming from lower levels of the abstraction hierarchy. And again, there's an anecdote about that, namely the computer game Civilization, which I myself played in my youth. Civilization, the human player chooses some country and rules that country through the course of history from Stone Age into the future. And the neighboring countries are ruled by the computer, by some rudimentary artificial intelligence rulers that are described by simple parameters. For example, India is ruled by Gandhi, and Gandhi is described by parameters such as very low aggression level. It is Gandhi after all. Another rule of the game, course of the game, is that when historically a country adopts democracy, then the aggression level decreases further by 2. So what happens when you play the game and your neighboring country, India, starts to develop democracy? Then Gandhi's initial aggression level of 1 decreases by 2, and thus the result is even negative aggression, so no aggression at all. Mathematically, 1 minus 2 is minus 1. However, in hardware, data type byte, which was used at that time for efficiency reason, 1 minus 2 incurs a wraparound, and the result is 255, very high level of aggression, leading Gandhi to wage war against its neighbor countries once India develops democracy. Which is kind of an anecdote. It's funny, right? But also it's technically a bug, right? And the reason for that bug is the confusion between hardware data type and mathematical data type. Mathematical data type, which was probably on the mind of the programmer at that time, being integers, 1 minus 2 is minus 1, whereas the implementation uses byte, hardware byte, where 1 minus 2 is 255. So that's another case of the benefit of abstraction, because nowadays in high-level programming language like Java, one has big int data type, which in software simulates the mathematical integers on top of the hardware bytes using a variable number of bytes transparent to the user program, executor, the interpreter, or the library underlying Java will allocate more bytes as needed on the fly just to avoid such wraparound errors. But that, of course, comes at a price, namely decreased efficiency compared to operating directly on hardware bytes. But since nowadays computers are roughly 1,000 times faster than at the time when I played Civilization game, this loss of efficiency is well afforded at the advantage of having no programming bugs, particularly when referring to more serious applications. So that being said, let's now recall about asymptotic efficiency, another aspect of the power of abstraction. So the mistake I fell when I designed the fastest bubble sort algorithm, which was actually the fastest bubble sort program on this particular Intel CPU at that particular time, is I fell for what Donald Knuth already had warned about. Premature optimization is the root of all evil. And what does that mean? It means that first one should focus on asymptotic efficiency, and only once asymptotic optimal efficiency has been achieved, the last virtue of computer science, then one may move on to optimize the constant factors that are commonly hidden in asymptotic notation. And to illustrate that point, here you see a table of 5 hypothetical computers. On the right, you see a contemporary computer with a gigahertz clock that means one operation takes roughly 1 nanosecond. The next computer is 1,000 times slower, megahertz computer, such as the Apple IIe or Commodore 64, with a clock of roughly 1 megahertz. Next computer is again 1,000 times slower with a kilohertz clock, 1,000 operations per second. This one has one operation per second, and this one is even more slower, only one operation every 10 seconds. And just for reference, the Konrad Zuse Z3 computer would execute roughly 10 operations per second. So it's somewhere here in between. So this is clearly and far ahead the fastest computer. However, in this hypothetical table, the fastest computer is running an asymptotically very inefficient algorithm, namely an exponential time algorithm, running time 2 to the n. Whereas the Apple IIe is running a cubic time algorithm. This hypothetical computer is running a quadratic time algorithm. This one an n log n algorithm, like for example, quicksort. And this one is running even a logarithmic time algorithm like binary search. And what we see from that table is that although this is by far the extremely slow computer, the asymptotically fast algorithm makes it dominate all other computers as soon as the input size becomes modest to large. Right? So here, for example, this one on input size 100 would take 40 billion years. Just for reference, our universe is only slightly less than 14 billion years old, but this would run for 40 billion years. Okay? Whereas this slow computer would just run for 1 minute because it runs the asymptotically fastest algorithm, although it is so slow. So the message to take away from here is really focus on asymptotic efficiency instead of absolute running time. Absolute running time is when you run your program on one specific input and you measure the clock and say it takes 1 minute or it takes 3 hours. But these empirical running time measurements have some serious disadvantage. One disadvantage is they only apply to this particular computing hardware, whereas if you run your algorithm on a different hardware, it could and will behave entirely differently. Secondly, it only applies to this particular input. So if you run that program, that algorithm on a different input, it can and will in general also behave very differently. So all these contingencies are taken care of and taken away when performing algorithm analysis, as opposed to empirical program evaluation. And the focus in this course is on asymptotic efficiency for simplicity, right? So imagine an algorithm whose running time is 17 times n cubed plus 5 times n squared plus 100 times n, and so on. It's a very complicated expression, but of course, asymptotically, this is simply a cubic time algorithm and much more concise and simplified a way of describing the asymptotic efficiency of this algorithm, ignoring all the lower order terms. And here you see some examples of asymptotic growth, classes of asymptotic growth, and corresponding picture, recalling the lambda big O notation from discrete mathematics, constant growth, logarithmic growth, sublinear growth, linear growth, quasi-linear growth, quadratic, cubic, polynomial, super polynomial, exponential, double exponential, and furthermore. And of course, the algorithm we want to design to have as low asymptotic growth as possible, and to prove that this is an optimal algorithm. There is no algorithm solving the same fully specified problem with lower asymptotic growth. Good, so that's about asymptotic growth, and I promised you an example about the importance and of problem specification, and an example about the importance of proof of optimality, and this is what we're going to do next. Both examples revolve around the exhausted problem of sorting. You know already all about sorting algorithms from introduction to algorithm. But to give you an example of the importance of specification, here's one example specification, right? So first we fix the setting. The setting is a set X equipped with the total order, right? We need a total order. Otherwise, the sorting problem cannot be fully specified, right? If two elements cannot be compared, if it's only a partial order, then which one is supposed to be first? Also, the output, well, intuitively, output of a sorting should be the input in sorted order, right? Now, since there are repeated elements possibly in the input, we cannot insist on the output to be sorted increasingly. So to be careful, we have to say that the output should be non-decreasing, right? Less or equal. Furthermore, we don't want the output to contain any new elements, obviously, right? Sorting algorithm which introduces new elements is not considered solving the sorting problem, or an algorithm which drops some element from the input. So how can we formalize all these intuitively natural conditions just to make them fully unambiguous? And here's one way of doing that, namely by requiring that the output of the sorting problem is not the sorted data itself, but instead a permutation which results in the sorted data being sorted. So let me say that again. The output here is considered not the data itself, but a permutation, which then, when applied to the input data, results in it being sorted. So that's one way of specifying the sorting problem. Of course, you can, once you have the permutation, it's just a matter of applying it to obtain the sorted data. So in a sense, this is more general. Conversely, if the input has no repeated elements, then the permutation which sorts them is unique. But in general, there can be several permutations that sort data if there are repeated elements. So that illustrates the problem specification in the problem case study of sorting. And the other aspect I promised to is proof of optimality. So let's look into that optimality example. And you might recall the proof of optimality of, let's say, merge sort from your Introduction to Algorithm course. You might also recall that quicksort is actually not optimal. That's an important misconception. Quicksort naively also still has quadratic running time as bad as bubble sort, at least on some inputs. On some inputs, quicksort is fairly inefficient, unless particular care is taken when choosing the pivot element, which is used to split the array. Ideally, the pivot is chosen such that the array splits half-half, right? Half of the elements are smaller than the pivot, and half of the elements are larger than the pivot. But how to find this pivot is, in turn, quite intricate problem. And there's a famous linear time median algorithm with two subroutines calling each other recursively. And since this can be done in linear time, which is highly non-trivial, that yields a good pivot for deterministic quicksort whose running time indeed is n log n also in the worst case. But other more naive ways of choosing the pivot still result in certain inputs in the worst case where quicksort becomes a quadratic time algorithm. So long story short, we have now two sorting algorithms that reach the lowest running time we know for sorting, namely n log n. And the question is n log n optimal, or can we have an algorithm even faster, sorting even faster than n log n? And the proof that you may recall is that any comparison-based algorithm necessarily must have running time at least n log n asymptotically. And I want to recall that proof for your convenience. And the proof involves certain class of algorithms, namely so-called decision trees. Decision trees for sorting. Here you see a decision tree for sorting 3 elements. So the input elements are A1, A2, and A3. And the algorithm, decision tree algorithm, first compares A1 and A2. If A1 is less or equal to A2, then it proceeds to the left in this tree. Otherwise, it proceeds to the right. And then, adaptively, depending on the outcome of that comparison, it would next compare A2 to A3 in this case, whereas in the other case, it would compare A1 to A3. And then proceed down in that tree accordingly until arriving at a leaf. And the leaf here is labeled with a permutation. Remember, the output of our sorting problem, the way we have specified it is that the output should be a permutation. And these permutations are written here into the leaves of this decision tree for sorting 3 elements. Here, for example, the output is the identity permutation. Here, the output is the reverse, 3 to 1, and so on. And you can verify that for any input, when following the semantics of this decision tree, the leaf that the algorithm ends up indeed contains a permutation that results in the input data to be sorted. Let me give an example. Let's suppose the input is 1 to 3. Okay, so comparing A1 to A2, comparing 1 to 2, 1 is less or equal, so the algorithm will proceed here. Then comparing 2 to 3, again, less or equal, so the algorithm will proceed here and output the identity permutation. Indeed, this identity permutation sorts the already sorted input 1 to 3. Another example, let's suppose the input is 3 to 1, which is not sorted. In this case, the first comparison results in the algorithm proceeding to the right because 3 is greater than 2. Then comparing 3 to 1, 3 is greater, so it proceeds to the right again. Then comparing 2 to 1, again, 2 is greater, so it proceeds to the right. So in this case, the output of this sorting decision tree is the permutation 3 to 1. And if you apply that permutation 3 to 1 to the input, which was, as you recall, 3 to 1, it will result in the sorted permutation 1, 2, 3. And so on for all other possible inputs and all possible leaves. So the general setting is we define a decision tree for sorting elements to be a binary tree. You see here it's a binary tree whose internal nodes are labeled with tests. Here the tests are called compare the ith element in the input array to the jth element. Here these are called A, I, and AJ. And the leaves are labeled with permutations in such a way that every input ends up, according to the semantics that I've just explained, ends up in a leaf whose label, permutation, results in the input becoming sorted when applying the permutation to that input. Sorted meaning non-decreasing. So that's a formal definition, a mathematical definition, and you already notice that designing and analyzing and specifying algorithm involves a lot of mathematics and logic. And there's a famous paper that explores that connection. No, there's entire books that explore that connection between computing and mathematics. But let me cut that story short and move on to the proof. The proof that any comparison-based sorting algorithm must conduct at least n log n comparisons asymptotically. And the proof is a combination of 3 items in a lemma. So again, very mathematical, and we're going to start with the third item, which is simply a mathematical observation that a binary tree with n factorial many leaves has depth at least the binary logarithm of n factorial. Well, that's obvious, right? Because when we talk about binary tree, it means that the number of nodes on each level can at most double. So root is 1, then there are 2, then there are at most 4, then there are at most 8. And if this has depth d, then at depth d, there can be at most 2 to the d nodes. But the hypothesis that has n factorial nodes, so solving means that the depth must be at least the binary logarithm of n factorial. And now we invoke Stirling's approximation, which says that the logarithm of n factorial is asymptotically the same as n log n. So that's the third item of our lemma towards proving that any comparison-based sorting algorithm must have depth at least n log n. The next item is item A, which is connects kind of between computer science and mathematics. Namely, it says that these decision trees that we introduced here are kind of universal for comparison-based sorting. Namely, it says that every comparison-based sorting algorithm can be unrolled into such a decision tree. Now, unrolled here is in quotes because that's not entirely formal. What it means basically is you execute your hypothetical comparison-based sorting algorithm symbolically. You execute it and check what is the first comparison. First comparison, since it's comparison-based, is compare 2 elements of the input array. That will give the root. And then continue symbolically executing the algorithm in 2 consecutive cases, either if the result of that comparison is positive, or if it is negative. In either case, the algorithm may then compare two other elements or the same element in the array, resulting in two successor nodes, two children's comparisons, and so on, until in the end, the algorithm outputs the purported permutation, sorting the data according to the specification, and we will write that permutation into the leaf of that tree, and thus we obtain a decision tree from any comparison-based sorting algorithm. Notice how important it is that we talk only about comparison-based sorting algorithms. Also observes that the running time of that initial algorithm corresponds to a bound on the depth of that tree, because each comparison we simulate symbolically results in one additional level in that tree. And if the algorithm has running time t of n, then after at most t of n levels, the algorithm will have terminated and output a permutation, and thus we will have reached the leaf and label that leaf with that permutation when converting a comparison-based algorithm into such a decision tree. And the final item for putting things together is again purely mathematical observation, namely that if we feed that decision tree with different permutations, then different permutations end up in different leaves. And that's because every permutation input has a unique permutation which sorts it, namely its inverse. In order to sort a permutation input, the output must be the inverse of that permutation. And since every leaf has only one label, it means we need to end up in different leaves when inputting different permutations into that. And now we put things together because we know that there are n factorial many permutations of n elements, right? That's combinatorics. So we know by item B that decision tree sorting n elements, including sorting all permutations, must have n factorial many leaves, namely different leaf for each permutation, for each inverse permutation, and therefore must have depth n log n. On the other hand, by item A, any comparison-based sorting algorithm with running time t of n can be enrolled in such a decision tree, and therefore the depth t of n must be at least n log n by item B and C, and therefore also the running time must be at least asymptotically n log n. And thus, we conclude the well-known proof that any comparison-based sorting algorithm must have running time at least n log n. Emphasis here is on comparison-based, because if you recall, there are other algorithms that are not sorting algorithms that are not comparison-based, such as radix sort, for example. Okay, now we have illustrated problem specification, first virtue of computer science, and proof of optimality, last virtue of computer science, and the trivial, or admittedly trivial problem of sorting. But this is for motivation and illustration purposes, when in this course we will specify and prove optimality of more advanced algorithms with respect to advanced notions of efficiency. So that leads to the goals of this course: design and analysis of algorithm, where analysis pertains to different notions of performance. So there are various modes of algorithm analysis, and the one you're all familiar with is worst case analysis. Worst case, as quicksort I just mentioned, with naive pivot choice, has quadratic running time unless you pay particular efforts to find a pivot more sophisticated way. However, even with a naive pivot choice, on the average, quicksort has n log n running time. So the worst case is a considerable overestimate of the performance. It's a very conservative way of analyzing algorithms, and may not be entirely realistic, because that worst case can, and in the case of quicksort actually is, very rare. So for more realistic prediction, one may want to conduct an average case analysis. For randomized algorithms, one conducts expected case analysis. Then for data structures, amortized analysis. For online algorithms, competitive analysis. For approximation algorithm, approximation ratio analysis, and so on. So various different ways of analyzing algorithms beyond the traditional worst case paradigm for getting a more realistic impression of the actual performance of the algorithm when implementing and running it on hardware with given inputs. Moreover, in Introduction to Algorithms, we focused on running time. That means sequential running time. But of course, there are other important cost measures, so-called cost measures, that may be more important depending on the application. For example, sometimes you might be more focused on memory efficient algorithm than on runtime efficient algorithm, because if your algorithm exceeds the memory that your computer is equipped with, then it cannot run at all. And this can happen easily. For example, if you consider routers in the internet, right? The routers easily process gigabytes or even terabytes of data, and there's no way to store that. So we really need memory efficient algorithms in some cases, and may even be willing to sacrifice running time just to get down the memory use. Other notions of algorithmic cost include parallel runtime when we talk about parallel algorithms. In this setting, also maybe communication volume is more important than the actual running time in case communication is the bottleneck. Or a number of processors. If your algorithm is a very efficient parallel algorithm, but it needs like thousands of processors, then even the best contemporary CPUs don't have enough cores to support that algorithm, and all the benefit of parallel algorithm is wasted, as opposed to maybe an parallel algorithm which looks less efficient in terms of running time, but which needs fewer processors or less communication. So all these are important aspects that we will explore in this course, building and on top of and going beyond the undergraduate Introduction to Algorithm course. So here we have some cost measures, and we have different ways of analyze. And the purpose of all this is to get an estimate, a prediction on the behavior of the algorithm before actually executing it, right? That's as opposed to empirical evaluation, where we first implement the algorithm, then running it on some input data. But that empirical evaluation is limited to the particular hardware that we used, whereas algorithm analysis is independent of hardware details. Also, it's independent of the input. It only depends on the input size, whereas different inputs may result in different behavior of actual implementations. So the purpose really is to have some independent assessment of the quality of the algorithm that is independent of the particular input, independent of the particular hardware. Yet it should be realistic, but it also should be simple. And that's often conflicting goals, because if we want the best precise prediction, then maybe this will be very involved, both in terms of analysis and also in terms of stating the result. That's why we use, for example, asymptotic notation, where we ignore constant factors and we ignore all lower terms to make it simpler, but also less realistic, because asymptotically it may look like, for example, quick sort and merge sort have the same performance, and they do, but only asymptotically. The constant factors actually differ. Final reason for performing algorithm analysis is to indicate whether it's possible or not to improve, whether we should start over and try to devise a more efficient algorithm, or whether we've already arrived at the provably optimal algorithm, the last virtue, and only then we can and maybe even should start trying to optimize the constants according to Donald Knuth's having avoided premature optimization. So just to give you an impression on this trade-off between realism and simplicity, as I said, that's one of the reasons why we consider big O asymptotic analysis, or sometimes even we just say this is a polynomial time algorithm and don't even care about the degree of the polynomial, which is of course even simpler than stating the polynomial itself, but also less realistic, less accurate a prediction. Then when we analyze the algorithm, we might simply count the number of operations, but a better assessment is to assign cost to each operation depending on the magnitude of the data. For example, when a comparison, if we compare two large integers or two small integer, it will take different running times, so only counting the number of comparison operations, as is common in sorting algorithms, can be misleading. And in some cases, that's why radix sort can be more beneficial in some cases, which takes into account the bit length of the integers to be sorted. And then in terms of memory access, there's an entire memory hierarchy. So the registers in a CPU can be accessed almost instantaneously. But then there's the level 1 cache, level 2 cache. Then there's the random access memory of usually size gigabytes. And then there's external memory, which can easily range up to terabytes, but which is much, much slower to access than registers or cache values. So for a realistic prediction, one can and maybe should take that into account. But of course, that makes the analysis much more involved and also affects the design of the algorithm. If we want to design memory efficient algorithm or algorithms that are aware or use the memory hierarchy, that's an entirely different goal than just designing algorithm that use a few number of operations, ignoring the cost of each operation itself. So after all these motivations and philosophical considerations, let's now move towards the end of today's session and conclude with an overview of the 10 chapters of this course. The first chapter is what we're currently talking about. Then we'll talk about tree data structures, which is a recap from your course on data structures. And we do that because we're going to analyze these tree data structures in average case and in amortized case. Now, average case and amortized case are in a sense similar, but they're also subtly and importantly different. And the similarities and differences will be something we'll talk about in these chapters 3 and 4 respectively. Then we'll move on to randomized algorithm and expected case analysis, Monte Carlo algorithm, and for example, then we'll talk about online algorithms and their competitive analysis. Then we'll move on to approximation algorithm, but to motivate them, we will first briefly recall that some problems are NP-complete and therefore cannot be expected to be solved exactly in polynomial time, but some of them can be approximated in polynomial time. Some even have approximation schemes, and others probably cannot be approximated unless P is equal to NP, approximation algorithm. Then we'll talk about parallel algorithms analyzed in parallel time. And finally, we'll talk about memory efficient algorithms. So that's the overview. That's a perspective of what you can expect in this course. Some administrative matters. The course has a homepage. Here's the course homepage. Some assignments you will be asked to prove, to analyze, to design and analyze algorithms. Other homework assignments, you will be asked to implement algorithms and to evaluate them empirically in order to get a really physical experience of what it means for an algorithm to be efficient or to be inefficient. Namely, if you run out of patience, that's a good indication that the algorithm is inefficient. And for these, half of the assignments will thus be practical assignments, programming assignments, which are conducted in ELIS. And this is the homepage of the ELIS system that we use for this purpose. Finally, we make use of KAI's learning management system, KLMS. So please make sure to get all announcements and to be encouraged to ask questions and to join discussion on KLMS. And finally, some pedagogical remarks. This is a quote from Konrad Lorenz, who received the Nobel Prize in 1973 about all the pitfalls of teaching. I mean, what a teacher thinks is obvious, but doesn't say, may not reach the pupils. And even if what the teacher says it may not be heard because maybe pupils are distracted playing on their smartphone. If they hear it, they may not understand it and fail to ask questions. And just even if they understand it, they may not believe it. What is believed may not yet be advocated. What is advocated may not yet be acted on, and what is acted on is not yet completed. So there are so many stages in the learning, teaching, and learning process that can go wrong. And so I will try hard to get around all these obstacles. And I hope you also try hard and focus. And what I'm particularly interested in is in moving up to higher levels of Bloom's hierarchy of cognitive learning. So here you see Bloom's hierarchy of cognitive learning, where knowledge is the basis. So it's very important to acquire, to accumulate knowledge. But this is also something that a memory stick can do very well and arguably even better than you. What you and I want is, of course, to reach higher levels beyond memory stick, namely comprehension, application, analysis, synthesis, and even evaluation. So in this course, I will try hard to convey more than just knowledge, namely comprehension and application. And similarly, the homework assignments will be designed towards these higher levels, and also the exams, midterm exam and final exam, will aim for the second and third level and take for granted your ability to amass raw knowledge. So that's all for this first chapter 1. We talked about philosophy of science and its application to computer science with the virtues of computer science and its differences to electrical engineering. We talked about the power of abstracting, being able to ignore lower levels in order to better focus on advanced layers, such as designing a sorting algorithm rather than first start by coding as I did. Hardware versus mathematical data types, the importance of asymptotic efficiency and classes of asymptotic efficiency, and only then, after having found an optimal, provably asymptotically optimal algorithm, then one can start optimizing constants. We've talked about two aspects of the virtues, namely problem specification before starting to solve it, and last item, optimality of an algorithm, at the example of sorting, namely specifying that the output of a sorting problem in our case should be a permutation rather than the sorted data, and then concluding that any comparison-based sorting algorithm must necessarily have running time at least n log n. We talked about the how and why of algorithm analysis, namely focusing on cost measures beyond running time, such as parallel running time or memory, and focusing on methods of analysis, such as beyond worst case, such as average case, amortized case, and so on. We gave an overview of the 10 chapters of this course and some administrative matters such as LEs and KLMS and the course webpage. And finally, I mentioned some pedagogical consideration and teaching philosophy. And that's all for today. That's all for this chapter 1. Thank you very much for your attention and interest. And I hope to see you again next time when we start with chapter 2, recalling 3 data structures. Thank you.